Alright, boys and girls, this will be our first lesson on simple machines with IMA and AMA. We're going to look at all six simple machines here and kind of go over what they mean and how it applies to ideal and mechanical advantages. And then I'm going to try and go through and solve a little problem here for it and make sure we're all on the same page. So to kind of start off here, when looking at ideal and actual mechanical advantage, we need some information first. We've already gone over now the lever styles, first, second, third class levers, what they all mean. What is important here now for this is understanding what we're trying to find here. So if you recall, IMA is equal to dE over dr, and AMA is FR over FE. Now, so we're on the same page here. E is effort, R is resistance, and then D for IMA is distance, whereas AMA looks for the forces that are applied. So force of resistance, force of effort. In a first class lever, we're looking at the possibility of being above or below 1 for our IMA. And in this case, it's simply measured as saying from the effort force over to the fulcrum, the distance here versus the distance of the resistance. So I'll just label it as an E and an R for clarity on that. There's our effort distance. That's our resistance distance. Second class lever, we have an effort distance here and a resistance distance here. Now if you'll notice on the first class lever, now the fulcrum can be placed anywhere on this entire line, which means that the effort can be shorter or longer than the resistance can be. In a second class lever, the effort is always longer than the resistance. Okay, and then the third class lever, the effort is always shorter than the resistance is itself here. So kind of label this out as well. Okay. In a first class lever, the IMA can be either greater than, less than, or equal to 1. In a second class lever, it has to be always greater than 1. And then in a third class, it will always be less than 1. Now, in an inclined plane, this guy is kind of different. This is a triangle, essentially. The resistance is always going to be the height that you are overcoming. And the effort will always be the hypotenuse of that triangle, the distance you're actually traveling. So every inclined plane ever will always have a longer distance than its resistance, because in a triangle, the hypotenuse is always longer than the actual legs. So effort will always be higher in number than resistance, which means that the IMA will always be above 1. A wedge is similar to an inclined plane. In a wedge here, our effort is measured as the height, and our resistance is measured as the width. Now, in the two first examples here, there's a narrow one and a thicker one. Which one do you think would be easier to push through an object? If this one here has a smaller resistance, but the same effort distance, that would mean that this one would have a better IMA. So this one would be easier. So the narrow, long wedges have a better mechanical advantage. Now, the same thing applies over here on this wedge, on the last one shown here. It's a bit different, a bit of a different shape here, but we still have the same resistance shown here, and then effort is the overall height of the wedge. Okay, so measuring those and then putting dE over dr, you can find the IMA of a wedge. Now, a wheel and axle, there's two variations here, either the wheel driving the axle, as in the first case here, or the axle driving the wheel, as in the case over here. Now, in each situation, we have diameters or radiuses to work with. In the first situation, we're going from a large diameter to a small diameter, so the large diameter wheel is the effort, and the small diameter axle is the resistance. And in the other situation, it's the opposite way around, like so. In the first situation, the IMA will be above 1 because the effort is higher than the resistance is. bigger number. In the other situation here, it'll always be less than 1. Okay. Just to kind of review on that really fast, you'd say dE and dr, right? Well, dE could be solved as the radius or the diameter, perhaps. I can say dr, that would be either the radius or diameter of the other shape. So if I was looking at the first one here, let's say if this was a radius of 6 and this had a radius of 1, we'll say, it would be then 6 over 1 because the effort is the larger wheel and then the radius of 1 is the smaller axle. Now in a screw, it's a bit different here. We have a thread call out, and you'll see we have a half 13 UNC thread. That is a standard call out for a bolt of some type. And what this all means, the first part here is the diameter of the bolt. The diameter of the bolt, which means that the diameter of this from here to here, that distance there is what we're looking at. That means that this bolt is a ½ inch in diameter. The 13 refers to 13 threads per inch, or TPI. And I'll get to that in a minute. And then the UNC is a standardized call out for a different type of thread. That one you can kind of ignore for right now. What's important to us right now is the 1/2 and the 13. Now we know that IMA is found as dE over dr. Well, what is the effort distance and what is the resistance distance in this type of system? Well, effort distance is the actual twisting around. So as you take a bolt and you turn it, twist it clockwise or counterclockwise, and as you twist it, the bolt will move up or down based on how you turn it. So it takes rotational motion and makes it go into a linear motion. So with the system here, if I have a bolt that I am going to rotate, say clockwise, the distance it travels around, the circumference of that traveling, is my effort distance. So I'll take the ½ inch diameter here and I'll apply that to my input effort distance. So my dE becomes the circumference of that circle. And that is found by saying diameter times pi. So I could say for my dE, I have 1/2 pi. That's my dE. My dr is unknown right now. And the resistance of a thread is based off of how far it travels up and down as you turn it. So if you turn the bolt one time around, how far does it move up and down vertically? And that comes from this threads per inch thing. So the TPI. Now down below here I've kind of drawn a little exploded view of that thread per inch area. So in here I've marked out we have 1 whole inch of distance being shown. If you were to count all of these little threads here, there are 13 of them in total. So that's what it's saying here, is that for every inch of distance on the bolt, for every 1 inch here, there are 13 of these threads for every 1 inch. Now, the distance it travels up and down is called the pitch. Now, the pitch refers to the distance between two threads. Oh, hang on, a little messed up there. There we go. That's the distance between two threads there, so it's the pitch. Now, if there's 13 threads for every inch, how do we find how far apart just 2 of them are? Well, if you think about the math behind this, it's simply going to be 1 over 13 because there are 13 threads for every inch, which means that for every 2 of them, the gap between the 2 would be 1/13 of an inch. So my dr is then 1/13. So my dE, we said, was 1/2 pi. My dr is now 1/13. That's what I would have for my mechanical advantage. Now, if you do the math for all this, we'll find it's a very, very, very high number. A screw will always net you a very high mechanical advantage. And the reason is because the pitch is so small. The dr is always a very low number. Now, in this example here, we have a wrench instead. If you're using a wrench or a screwdriver to turn the actual bolt or screw head or something like that, What matters there is the distance around that you're traveling now for the circumference of that. So if we have an input effort here, the distance between the center of the bolt and my effort distance is now, we'll say, 6 inches for the radius. Well, now my circumference is much bigger than the actual half-inch here. My half-inch bolt is no longer important now. What matters now is the whole distance around I'm traveling as I rotate this. So now my numbers in here will change. I would have 12 pi. The reason is that I have a radius of 6. Well, it's diameter times pi to find the circumference, so it'll be 12 times pi. Now my IMA has gone even further up because I now have a longer extension on my wrench. So that's how you would solve for the mechanical advantage of a screw. On the pulley systems here, I've given the 3 most popular versions: the fixed, the moving, and then the block and tackle. On these drawings here, you'll find there are some black pulleys, some solid black ones, and also some ones that have a white center. The solid black ones are fixed pulleys. They will not move up or down. They will stay stationary. The ones that are hollow are going to move up and down as the string is being pulled. So the simple trick to finding mechanical advantage of a pulley is really easy. All you want to do is take a pencil and draw a line through the system. Now you want to cross as many strands as you possibly can. All we're going to do from here is count. In a fixed pulley, we have 2 crosses. We have one crossing here and one crossing there. However, this first one is actually part of our input force. That one does not count. So all I want to count is the strands that support the weight. So this strand here is the only one that actually supports the load beneath. That would be, we have one strand supporting it. Our IMA is then equal to 1. In the moving pulley to the right of that, same thing here. Draw a line through the entire thing. Again, this first one does not count. It is not supporting the load. However, the ones over here and there are supporting the load. So we have 2 points of connection. Now our IMA is, as you probably guessed it, 2. This is a moving pulley. Now a fixed pulley is always an IMA of 1. A moving pulley, depending on how many pulleys there are in the system, can be more than 2 or just 2 sometimes. Block and tackle, same thing here. Line through. The first one is not a support strand. This one here and that one there, however, are. IMA of this design is also 2. So if we look at this a bit differently, let's go ahead and add another pulley down here. If I add another pulley down here and my strand goes around here, loops around and back again on this entire system, and I draw my line through here, I now have 4 points that it runs through there, which means my IMA is actually 4, because I have now 2 moving pulleys that will be moving up and down as I pull string through it. To do a quick problem here, I want to have you guys solve for either the effort or resistance distance based on the problem here. And the problem you can kind of see here as you read through it. I'm giving some information to you about forces, input force versus resistance force, and also I'll give you some information about the distance of the resistance as well. The first thing I want you to do is draw it out. So I kind of drew out a little sample here of how it might look when it's done in the sketch. It's a first class lever, so I have a standard first class lever shown here. I show that there is 15 newtons of input force, a 45 newton output resistance. I know that the distance between the fulcrum and resistance is 2 meters, and my unknown is the DE. Well, I know that AMA is solved by saying FR over FE, and IMA is DE over DR. So I'm going to go ahead and plug in some numbers here and start solving through this. I'm almost out of time on my video here, so I'm going to go ahead and stop this very shortly. I'm going to show the results of this, get an idea how this all works here. So on the first bit, AMA 45 over 15, it's FR over FE. My ratio is 3 over 1. To find the distances I want to look for, I'm going to simply set FR over FE equal to DE over DR. So I'm going to use this equation here to solve for what I want to try and find. When I plug those numbers in, 3 over 1, FR over FE equals X, our unknown, over 2 meters. I find that our distance is 6 meters, giving us the result that we need for this answer. You can do the same thing for any other type of problem like this as well.